Hello everyone and welcome back to Thermo Shorts for Lecture 7, where we're going to be looking more at how we fix states in thermodynamics so that we can find specific internal energies that we can plug into this version of the first law. So in this class, we talked about when we're dealing with water, it's important to be able to draw out what state we're in because we need to decide whether or not that water is a liquid, a vapor, or some combination of the two. So we draw this vapor dome on a TV diagram. And if we're liquid water, we're above the vapor dome and to the left. And if we are pure superheated vapor, we're above the vapor dome and to the right. But if we're under the vapor dome, we're some linear combination of saturated liquid and saturated vapor. So first, how do we fix states if we're either in the subcooled liquid region, A5, or if we're in the superheated vapor region, table A4? So here we'll use linear interpolation. For linear interpolation, in this case, I always define an interpolation factor A. And this is because as our temperature changes on the tables, we'll have two different temperatures. And what we're saying is we're going to assume that this is linear between these 2 points. So if I know my temperature range and how far across that temperature range I've gotten, that's this interpolation factor A, then I need to have gone the same percentage of the range for my two values of specific internal energy. So if I can find A using the temperature, then I can use A to find the specific internal energy. And we'll assume that all the properties vary linearly like this between 2 points on a given table. So here's an example where we're trying to find the state of water, particularly the specific internal energy when the pressure is 1 bar and the temperature is 400 degrees. So here we look on table A4 and we find the subtable where the pressure is 1 bar. Unfortunately, in this case, I don't have a temperature of 410 as a row on my table, so I have to interpolate. Here, I'm going to find that my value for my interpolation factor A is 0.25 because I'm a quarter of the way between 400 and 440 degrees. And then I put that into my equation and I get a specific internal energy as shown here on the screen. So that's a single interpolation, but sometimes we have to do double interpolation. And here we're going to have to interpolate with temperature and with pressure. The pressure we're trying to find here is 0.8 bar, but I don't have a subtable at 0.8 bar. I have one at 0.7 and one at 1 bar. So it's like I have to make my own table. The temperature that I want is 220 degrees, but the rows on these tables are 200 and 240. So I need to be halfway in between there. So in this case, I need two interpolation factors. You can see I could draw this out in two ways. One, if I interpolate first with temperature using this interpolation factor B, saying that I've gone, in this case, halfway for the temperature range at both my pressures. Then I'll do my second interpolation with pressure using this interpolation factor B, which is determined by the difference in the actual pressures that I have on the table and the pressure that I'm looking for in my problem. In this case, what I like to do is make my own table. So here I have one pressure that's on the table, the other pressure that's on the table, and then the pressure that I'm looking for in the middle. I have one row of temperatures that's on the table, another row, and then what's the temperature that I'm looking for. So here I can put the known values from the table in the corners, and where I want to be is I want to get the answer at the center of my new table. I can also do this problem interpolating first with pressure and then with temperature using the same interpolation factors A and B. Again, I'd want to make my own table, but here I would interpolate first with B and then I'd interpolate with A between these two rows. In these double interpolation problems, I'm always hoping that either A or B is 0.5, because if it is, then I can just take the average of the two known temperatures in that direction. So if I have one of my interpolation factors that's 0.5, that's the one that I'm going to do first, because as you see, the interpolation factor I choose to use first, I have to use twice. In this case, you can see we're trying to use B, so I have to use it once at T1 and then once at T2. So here's another example, right? The pressure is 0.8 bar and the temperature is 220 bar. So I have two different interpolation factors. My interpolation factor A with temperature is 0.5. My interpolation factor B with pressure is 1/3 or 0.33. Here, because 0.5 is 1/2, I'm going to do that one first because that means I'll do it twice and I can just take the average of the numbers. So in this problem, first I'll interpolate with temperature at the lower pressure. I know my interpolation factor is 0.5. So I'll do the interpolation and I find a value for the specific internal energy at 0.7 bar and 220 degrees. I put that up on my table. I do the same thing at the higher pressure. Here at 1 bar, again, I get a specific internal energy that's at 200 degrees. So now I've done my two interpolations with temperature using my first interpolation factor. And now I have to use my second interpolation factor, 0.33, and interpolate between these two numbers that are on my table. Here I can now fill in the final specific internal energy, that's 0.8 bar and 220 degrees Celsius. Now I've answered this problem. So that helps us out if we're above the vapor dome, either to the left or the right. But what if we're under the vapor dome? Here, we're going to use a different table, either table A2 or A3. The difference is the order in these first two columns. On table A2, the temperature is first, and I have nice round temperatures, and it tells me the saturation pressure for each of those temperatures. But on table A3, it's like this, with pressure on the left, nice round pressures, and temperature on the right, where it tells me the saturation temperature for each of those pressures. Now, if my variable, whether it's any of these different intensive variables shown in the table, so when it's the subscript F, whether that's VF or UF or HF or SF, that's the saturated liquid value. So that's the liquid that's at the right temperature and pressure to boil, but it just hasn't boiled yet. So here, I guess the only tricky thing is when we're talking about the specific volume of the saturated liquid, we have to remember that this value has been multiplied by 1,000. So to get the real value, we have to divide by 1,000. We have the same values, but with the subscripts G, and the subscript G tells us that's what's going on at the saturated vapor. That's the far right-hand side of our vapor dome. So now we just have a linear combination of saturated liquid and saturated vapor if we're under the vapor dome. And that combination is given to us by quality. The definition of quality, it's my mass of vapor divided by my total mass. I can take that equation, and it's also true because this is a linear combination of saturated liquid and saturated vapor. I can also define X, or quality, as the specific internal energy at that quality minus the specific internal energy of the saturated liquid divided by the difference between the specific internal energies of the saturated vapor and the saturated liquid. I can rearrange this and get an equation that looks a lot like the equations I had when I had an interpolation factor of A. And that's why I like to set up those problems so that they look like quality. So here's an example where we have 0.8 bar and a quality of 0.9. Anytime you're told the quality, you know that you're under the vapor dome. In this case, because I know the quality, I can put in the values of UF and UG into my quality equation, along with my known quality, and get a specific internal energy. We did the same thing here. This is on table A2. Notice the temperatures are on the left and the pressures are on the right. Here we're told the temperature is 100 degrees Celsius and the quality is 0.25. We do the same process. The equation is the same, and we get a specific internal energy for this case. Now you can also get a bit of a trickier process like this, where they tell you the temperature is 100 degrees and the specific volume is 0.9. So what you have to do here is, again, I would look to see always if I'm under the vapor dome first. For 100 degrees, I have to decide if I'm between VF and VG. Now, remember, this is the tricky part here. This is not 1.0435. VF here is 1.0435 divided by 1,000. So in this case, even though it doesn't look like it at first glance, we are between these two numbers because this is this number divided by 1,000. So now we know we're here. I'm trying to find the specific internal energy. But to do that, I'm going to have to find the quality first because I'm not told the quality. But in this case, I can get the quality from the specific volume. So here I'm going to use the specific volume information I have to find X, and then use X to find specific internal energy. So here we can have the exact same equations we have for specific internal energy, but substitute specific volume, or little v over here. So that means I can find X because I know V of X, I know VF, I know VG, and I know VF. So here, I put the values I know about the specific volume into this equation for X. I find my quality, which is just over 0.5, and then I put that quality into this equation for the specific internal energy of a given quality. And when I do that, then I can find specific internal energy in this case. So hopefully that gives us an idea of how we can fix states or find specific internal energy for water in all of its three phases. Thanks for your time. I'll see you again next time on Thermo Shorts.